Hello, calculus fans! Right, so there's a few three-dimensional objects that we can compute the volume of rather easily. A rectangular brick, like a box. If it has height h, width w, and length l, then you can compute the volume easily, height times width times length. A right circular cylinder of radius r and height h has volume pi r squared h. Right? There's a right circular cylinder. Now, I would say that you're used to the word cylinder being applied to what we should really be calling a right circular cylinder. The word cylinder is actually very broad. Any object which has identical cross sections parallel to its base is called a cylinder. So it doesn't matter where we take this slice parallel to the base. No matter how high we go, we're going to get the same shape. So if the area of the base is A and the height of the cylinder is h, then the volume of the cylinder is A times h. And notice that with a right circular cylinder, the area of the base is pi r squared, which then gives us the volume of the cylinder. The volume of a cylinder is A times h, which is pi r squared h. And really, this is how I remember the formula for the volume of a right circular cylinder. Okay, now the question comes up, what if the object we're dealing with is not a cylinder? So let's suppose we have a solid object that we want to compute the volume of. So we're going to intersect this solid object with a plane. We get a cross section of S. You think like a loaf of bread and then you slice that bread. So whatever shape you get there, that's a cross section. So then we're going to let A of x be the area of that cross section that's in a plane perpendicular to the x-axis and passing through the point x. And x is some number between A and B. Now the book has a really good picture of this that I'm not going to try to replicate. You have to imagine a situation where you don't have a cylinder, you have some other type of object, you slice through it, and depending on where you slice it, the area of that cross-section is A of x. So we think of slicing this with a knife through x and computing the area of this slice. And the important thing is that this area might vary as we choose different values of x between A and B. When you have a cylinder, it's not supposed to vary. But when you have an object that's not a cylinder, then you could have different values of A of x. Think of like a French loaf of bread. When you cut it at the ends, you get very small pieces of bread. You cut it in the middle, you get big pieces. And so the area will vary as you move along. So now our book will give a description of slicing the solid into very thin slices. Each slice is actually really close to a cylinder. So when you have a loaf of bread and you slice it, even though the ends, the crust might be a little bit crooked, it's actually pretty close to a cylinder. And so we can add these up to get the total volume. So ultimately we're going to get this, and this is going to be our definition of volume. So as before, I'm going to say that I have a solid that lies between x equals a and x equals b, and I'm going to let A of x be the cross-sectional area of S in the plane P of x through x and perpendicular to the x-axis. So that's think of it as slicing your loaf of bread. A of x is the area of the face of the slice. So if this A of x is continuous, then we're going to define the volume of S to be the integral from a to b of A of x dx. And this is a definition of volume. All right, so the way we're going to see how this works is the volume of a slice is delta V, which is approximately equal to A of x delta x, because that slice, like the slice of bread, is very close to a cylinder, so I'm using the formula for the volume of a cylinder. Then to get the total volume, I have to add up all these slices. So remember that sigma means to add things up. So we add up all the total slices, and since each slice is about A of x delta x, This is the approximate total volume. Now, we're in a calculus class, so we take a limit as n goes to infinity. So n is the number of slices. And now we get some expression that looks like this. So we have a limit as n goes to infinity of the sum of all these a of xk star delta x. So these things here are the volumes of each, I think of this like a bread slice. And then this whole thing, the limit of this sum, this is a limit of a Riemann sum. And so we get this integral, the integral from a to b of a of x dx. And so that's essentially how the calculation goes. So really all we're going to do is remember that this is how I calculate the volume of some object if I can calculate the area of its cross sections. Okay, that's all for now.